Today we get to learn about function notation. It's when you have ordered pairs, and instead of listing out a whole bunch of ordered pairs, we write an equation instead. The equation is written in function notation. It's the same thing as when you start an equation with y equals, but with function notation, we're going to start the equation with f of x equals. So when you see something that looks like that, that's the same thing as seeing y equals, and it means that it's a function of x, that depending on what we put in for x, for our input, we will get a certain output value, a certain y value, depending on what we put in. So to read this out loud, you'd say the function of x equals f of x plus 3, or we would just say f of x equals 5x plus 3. So to figure out what your y value will be, what your function equals for whatever input you have, inputs are the x's, so you're just going to put in whatever your number is into the equation wherever you see the x. So if we were going to evaluate this function for x equals 1, x is our input. That means everywhere we see the x, we're just going to write a 1. So it would read f of 1 equals 5 times 1 plus 3. And then you would do the math from here forward. 5 times 1 is 5. 5 plus 3 is 8. So let's try some more. So here what they gave us is f of 0. That means we're trying to figure out what the function equals, what y is, when x equals 0, when x equals 1/2, and when x equals -2. We're trying to find all the y values that go with those numbers when we plug them in. So this is what we'll write. F of 0, what are we going to get for y when we plug 0 in for x? It's going to be 7 minus 2 times 0, because everywhere we see the x, we're going to plug in that number. Now we just calculate. It's going to be 7 minus 0, which is 7. So that means when x is 0, y is 7. Next, for the 1/2, f of 1/2. If we plug in 1/2 for x, what's the y value? 7 minus 2 times 1/2. That will be 7 minus, well, 2 halves makes 1 whole. So it's going to be 7 minus 1, which is 6. That means when x is 0, when x is 1/2, y is 6. We could be writing these as ordered pairs, but for these problems, you can just circle your final answer, like I'm doing. The last one we have to try is f of -2. So what happens when we plug -2 in for x? It goes right there inside parentheses. This is going to become 7 plus 4, because a negative times a negative is a positive, and that will equal 11. That means when x is -2, y is 11. So go ahead and you try the same ones, f of 0, f of 1/2, and f of -2 for 1b. Next, I'll show you how to do 1c. We're still finding these values up here. So I'm going to write f of 0. So we're trying to figure out what y is when x is 0. So let's go to 0 on the x-axis. Here's the x-axis. It's the horizontal one. And we're not going to move anywhere forwards or backwards. We're going to stay on the x-axis. Well, how high is the graph when we are staying right here on the y-axis? Well, this is where the graph is. It's 4 units up. So that's the answer. Let's try this for 1/2. How high is the graph when x is 1/2? Okay, so we have to go to the x-axis. We're going to go over to 1/2. if that dash is 2, then this dash is 1, which means a half is going to be right in the middle. So where is the graph? Well, if we just go straight up to where we meet the graph, we can see how high up that is, and it looks like it's in between 3 and 4. So we will put 3.5 or 3.5 for the answer. The last one we will do is f of -2. Remember, we're still doing the ones from up there. So I need to go to -2 on the x-axis, which is right here. I'm going to see how high the graph is at that part of the graph, and it looks like it's up 2. So there's my answer. Okay, you try the same thing for D. So remember yesterday how we had some graphs that looked like dots, and today we see some graphs that are solid lines? Well, there's a difference between the two and how they're represented. Sometimes you're going to graph things and connect the lines, sometimes you're not, and this is how you tell. Graphs that are solid lines, like the ones you see here, can be evaluated at any x value. That means that we could figure it out when x equals 1/2, like you had to do in 1D. We could figure it out when x equals -1.1. We could go to that spot and figure it out. We could figure out where the graph is at -2.5. We'd be able to do that because the line is everywhere on the graph. It even continues because of the arrows at the end. So if that's what you have, even in weird decimal places, your graph is continuous. Graphs that are continuous are represented by equations in function notation. So if you see f of x equals, or y equals, you're going to have a continuous graph, unless they state otherwise. They might exclude some values, like they'll say x does not equal 2 or something like that, and then you'd make a hole in the graph there, but we don't need to worry about that for today. If you have a graph that is made up of a bunch of dots, and you can only figure out particular x values because it skips around, those would be like graphs we were looking at yesterday. Those graphs are called discrete. You know you'll have a discrete graph if you are putting a mapping diagram on a graph. Remember the thing with the two sections with the arrows? If you have a set of ordered pairs, or if you have a table of x, y values. So that's when you'll have discrete graphs with dots. Any other time, if you have an equation like that, you'll have a continuous graph with a solid line. It's up to you whether or not you need to connect the dots, so pay attention. Now we're going to practice graphing. So let's take this mapping diagram, and by the way, since it's a mapping, we already know that our graph needs to be discrete, so we're going to use dots. And first I'm going to write the ordered pairs. So I'm going to take 3 for x and put it with 2 for y in an ordered pair. I'm going to take the 5 and put it with 6. The 7 will go with 10. And the 9 will also go with the 10. By the way, this is a function because none of those x's repeat. So let's plot those. We're going to go 3 over on the x and 2 up on the y. There's the first dot. Next we will go 5 over on the x and 6 up on the y. There's the dot. 7 over and 10 up all the way to the top, and then finally 9 over and 10 up. That's it. Do not connect the dots. We can verify by looking at the graph. None of those dots are stacked up. It is a function. It wasn't asking us if it was, but it is. Next, I'm going to walk you through 2b because this one is its own different kind. So what we're going to do is, first of all, you might already be thinking, since we have a function equation, this is going to be a continuous graph, so it'll be a solid line, if you want to make yourself a note, because we have function notation. So what we're going to do is, for this equation, we're going to plug in these particular x values into the function and see what we come out with for our y. Remember, y and f of x are the same thing. So let's plug in -2, where x is. So it'll be 2 times -2 plus 1. Well, that's going to be negative 4 plus 1, which is negative 3. That means when x is negative 2, y is negative 3. So we have the ordered pair negative 2, negative 3. Next, we'll plug in negative 1 for x. So it will be 2 times negative 1 plus 1. That'll be negative 2 plus 1, which is negative 1. That means when x is negative 1, y is negative 1. There's our second ordered pair. Next, we'll plug in 0. 2 times 0 plus 1. That will be 0 plus 1, which is 1. So we have the ordered pair 0, 1. Next, we'll plug in 1. 2 times 1 plus 1. Well, that will be 2 plus 1, which is 3. 1, 3 will be the next ordered pair. And finally, 2 times 2 plus 1, that gives us 5. So 2, 5 is our final ordered pair. Now we will plot them on the graph. So negative 2, back 2, down 3, back 1, down 1, 0 left and right, but up 1, 1 over, 3 up, and finally 2 over, 5 up. So those are the ordered pairs, but we will connect them with a solid line because we didn't have to pick those. We could have picked negative 0.5, we could have picked decimals in between those, we could have picked any number, and so that's why it's continuous. The last thing is to take what we learned a few sections ago about writing algebra from words, and now writing the words in function notation. So we have a Japanese bullet train that averages about 156 kilometers an hour. We'll need that number. The distance from Tokyo to Kyoto is 380, so that's how far we have to go. Our function is going to represent the distance, we'll use a d to represent it, remaining on the trip t hours after departure. So we're trying to figure out what happens to the distance remaining. Well, once we start the trip, the more time goes by, the fewer miles we have left to go. So the distance remaining depends on how long we've been traveling. So distance is a function of time. So we're going to start off just like that. The distance remaining depends on how far we've been traveling, or how long we've been traveling. If we haven't started the trip, we have all 380 miles to go. The distance will decrease, right? We're trying to find what's left the longer we are on the trip. So we're going 156 miles an hour. That means we'll multiply 156, our speed, by how many hours we're going. And that'll be it. So what would happen if we put in a value of 1.5 for x? Remember, x's are the input. What would that look like? Well, it means we would take 1.5 and put it where the t's are. Sorry, I should have said when t equals 1.5. So we'll erase that and put a t. We'll just replace it right in the equation. It will look like this. d of 1.5, we're going to put in 1.5, equals 380 minus 156 times 1.5. When we figure that out, we get 380 minus 234, which equals 146. That means that after we've been traveling for 1.5 hours, for an hour and a half, it means there's 146 miles left to go. Number 2B will be very similar. So good luck, and we'll see you tomorrow.